Hello, myself Vivek Dur. In this video, I am going to explain the modeling and analysis of block type machine foundation by finite element method using Barkan's model. First of all, I will give a brief introduction on machine foundations. Machine foundations form a vital part of any industrial complex. Its initial cost is less, but its failure can break a whole process line and can cause a huge loss to the industry. Hence, machine foundation needs to be carefully analyzed and designed. There are mainly two methods for deciding machine foundation: Barkan's method and elastic half-space method. Barkan's method is recommended by IS 2974 1982 and elastic half-space method is recommended by ACI 351.3R. It is an American code. In Barkan's method, the embedment effect and the soil damping are not considered, whereas they are considered in elastic half-space method. But as it is recommended by Indian Standard Code, we are going to model the machine foundation using Barkan's method. And dynamic analysis of machine foundation system is trial and error based process, and it is very complex. Hence, finite element is the most commonly accepted analysis tool for dynamic analysis. The analysis and design of machine foundation requires more attention since it involves not only the static loads but also the dynamic loads caused by the working of machine. The vibration response of the machine foundation soil system is defined by its natural frequency and amplitude of the vibration. So in this video, I am going to show the modeling of machine foundation by finite element method in a STAAD Pro software, and after analysis we are going to determine the natural frequency and amplitude of the foundation. So let us take an example. So first of all, we will require a machine data. Machine data is generally provided by the machine manufacturer. As you can see, this data is of a reciprocating machine. It is mounted vertically, hence it will produce dynamic forces in vertical direction, in horizontal direction, and moment about horizontal axis. So the operating speed is 250 rpm, weight is 100 kilonewton, vertical dynamic force is 2.5 kilonewton, horizontal dynamic force produced is 2 kilonewton, horizontal dynamic moment is 4 kilonewton, and the machine center line lies 0.15 meter above the top of the foundation. Next thing we require is soil data. That is bearing capacity, design coefficient of uniform compression, and Poisson's ratio of the soil. The coefficient of uniform compression we get from the geotechnical reports, and it is obtained by performing a cyclic dead loss test on the site. The coefficient of uniform compressor that we get on site needs to be converted to design coefficient as the size of plate and the base area of the foundations are different. So in presently we are taking directly the converted value of Cu, that is 75,000 kilonewton per meter cube. Next we require is the foundation data. So as I told that it is a trial and error based process, we need to select any arbitrary dimension of foundation and check it if it's safe and satisfies all the codal criteria. And if not, we need to change the size of the foundation and reanalyze it. But in this video, I had already finalized the size, and I am going to show the foundation and model a foundation and analyze it as per this dimension. This is the geometry of the foundation. Plan and elevation are shown in the figure, and we are going to model exactly the same foundation in STAAD Pro software. So let's start. This is the STAAD Pro Series 6 software. New project, structure 1. Machine foundation. Select the path where I want to save the file. Next, finish. First of all, I will have to make a small cube, and it will be an element which will be used to form the whole foundation. So my foundation is 4 meter cross 3 meter. So I will take an element of size 0.25 meter in length, width, and height. So first of all, I will have to write the coordinates over here. So I will write it. As we can see, as I am writing coordinates, we can hit the screen displays the nodes. Here are the 8 nodes. Now I am selecting solid options over here and select all the 8 nodes. One by one, and the cube is ready. Here I can see the dimension of the cube. Dimension of cube is 0.25 meter. Now I will select the solid cursor, select the cube. Now as we know that the length of the foundation is, it was 4 meter, right? So how many elements I will require is 4 divided by 0.25, that is 16 elements. So I already have one element, so I will have to repeat it for 15 times. So I will write here 15. Okay. Now again I will have to repeat this width-wise, so geometry, transformation, repeat. In Z direction, default step spacing 0.25, as the size of cube is 0.25 meter. Number of steps will be 3 divided by 0.25 is 12, so I will write here 11. Okay, so again we have to copy it in vertical direction, so again I will go to geometry, translation, repeat. Here y is the vertical direction. I will write default space spacing 0.25. Number of steps I will write 2. Okay, so here it is ready. I need to delete some cubes over here, as the height of the first block is was 0.5 meter. So I will select the solid cursor. All the cubes are selected. Press Alt VV. Top view. I have to select the two cubes from all the sides, because this was our geometry. The block that is below is 0.5 meter high, and the second block above it is 1.5 meter. We will go to STAAD Pro software. I have to deduct 0.5 meter from all the sides. Here they are related. Now the height of the second block is 1.5 meter, and 1.5 divided by 0.25 is 6. So I will select all these and repeat in vertical direction. Here I will write 5 steps, 0.25. Okay, so here it is ready. Now I will view the full view. So as we can see that geometry of foundation is ready. You can see dimensions. Yes. Now next thing, we will go to general. over here and select the properties. Now first of all, we will have to draw the rigid beams. As you can see that the foundation is built up of small cubes, and after applying the force, the foundation should act as a rigid body. It means all the cubes should move with each other and not independently. So we need to connect them by a rigid beam. So here is a object of adding beam. At base we will select all the nodes. Press Alt VV. So here is it. These are the base nodes. I will draw a beam. I will draw beams at base. It connects the four corner and center. The whole view. Also, we know that the machine loads act on the machine CG line. So we need to insert a node at the point where there is a machine center of gravity. So we will write here the coordinates of that point. So it is 2.15, 1.5. As you can see, it is the node of machine CG. I'll select the nodes below the machine CG. VV, left view. So nodes exactly below the machine CG are selected. Now I will draw rigid beams to connect the machine CG point with the foundation. As we all know that machines are rigidly connected to the foundations, so machine also moves along with the foundation when the force is applied on it. This is the whole structure. Now we'll go to general, and in properties we need to define a property for the rigid beam. So we'll select rectangle 0.05 in both the directions. Here is a concrete. Before it, I have to define the material properties of rigid beam. We'll go to materials, create, title, I'll select concrete, and type here RIGID, rigid beam. So in rigid beam, I will just double the or increase the Young's modulus of the material. I will change 7 to 14 and here 6 to 13. The property of rigid beam is changed. Now it is very much more rigid than concrete and steel. And also I will make the density as 0. So while analysis, the weight of these beams are not calculated. And okay. Now I go to property, and I have defined the beam, edit and select the material as rigid beam, change, close. Now we'll select beam cursor, select all the rigid beams, and assign the rigid beam property, assign to selected beam, assign. Next we'll select the material, concrete, select the solid cursor on the left side, select all the foundation, assign to selected solids, assign. So material is already assigned. Now we will go to support. here we will have to create a support, and so create fixed word type support. As we know that foundation lines over the soil, we need the spring stiffness, hence the stiffness of the soils it should be converted into, it is converted into spring, and its stiffness in all the 6 directions should be inputted. So as we go back and look that we were having the value of Cu, that is coefficient of uniform compression, 75,000. So how to convert it into spring stiffness? So here we go. Design coefficient of uniform compression Cu is 75,000. So we will calculate coefficient of uniform shear, coefficient of non-uniform compression, and coefficient of non-uniform shear from coefficient of uniform compression value. So here are the formulas of it. Coefficient of uniform shear 0.5 Cu, coefficient of non-uniform compression 2 Cu, and coefficient of non-uniform shear 0.75 Cu. Next, for stiffness, we are having the formulas. These are the formulas for stiffness, the x, y, and z direction. Similarly, rocking, that is a rotation moment about x, y, and z direction. Here it should be z. By mistake, I written here x, and the x, y, and z directions are shown in here. We are taking y as vertical axis and x and z as horizontal axis. So we will calculate, this area is the base area of foundation, and this I-axis, I-y-y, and I-z-z are the mass moment of inertia of machine foundation combined. And so we need to calculate it manually, and also get the values of Cu, C tau, C theta, C phi, and C xi, and from it we can get the values of Kx, Ky, Kz, K theta, K psi, and K phi. So I had calculated it manually, and here the values are written. So we cannot input these values directly. First of all, we need to divide the Kx value. These are the translation stiffness. First, they are the translation stiffness, and it is to be divided by the number of nodes at the base of the foundation. So in a present model, there are total 221 nodes at the base, and so I will divide 328125 by 221, and the answer is 1484.73 kilonewton per meter. Similarly, for all the 3 stiffnesses, I will do that. Next, for rotation stiffness, no need to divide, but here we are having the values in kilonewton into meter per radian. But in STAAD Pro software, we need to input these values in the form of kilonewton into meter per degree. So we need to multiply these values by pi by 180, and we get the following values. So all these 6 values I am going to input in the STAAD Pro. So first of all, I will define 2 types of support. In first support, I will just write the translation values. There were 1484.73, 2969.46, and 1484.73. I will apply release in 4 moments. Now I will create the another support fixed part, and I will write the values of all the 6 directions: 1484.73, 2969.46, 1484.73, 11930.96, 13243.37, and 23384.68. As you can see, these values are as same as I had calculated over here all these values. Now the support 2, that is all the support that contains only this translation stiffness, it had to be assigned to all the nodes. I will select the base nodes of the foundation, press Alt VV. You can see set the base nodes. So what will I do? Assign it to selected nodes. Assign. As you can see, springs are assigned to each and every node. Now you'll see whole structure. The support 3 needs that contains the rotational stiffness. It needs to be assigned at the point which lies exactly below the combined CG of machine and foundation. In present case, the shape of the foundation is rectangle, and machine also lies at the center of the foundation. Hence, the combined CG of machine and foundation will lie exactly at the center. So we will select the center node at the base, selected node, and assign support 3. Assign to selected node. Assign yes. So you can see the symbol is changed, and support with rotation stiffness is assigned at this. So the springs are assigned. That means soil is also modeled below the foundation. Now we have to assign the loads. First of all, then we will go to load and definition. So definitions, time history, select time history definitions and add. So as we have in the machine will always have a harmonic function. Select harmonic function. Select force over here. As in this machine, it is a cosine function. This we get from the machine manufacturer. This data. Select RPM and write here 250 as the machine is of 250 RPM. Amplitude. So amplitude, that is the force that was acting. So the force was acting as 2.5. First force in vertical direction. Phase here we will take 0, and cycles we will keep 100, and this step we will keep 0.00125. That is steps per cycle, and add. So one force is added. Now we have to add another force, that was 2 kilonewton. It is for horizontal force. Add. Third was a moment about horizontal axis. So I will select moment, and it was of 4 kilonewton into meter. Add. Next we will have to define the damping. As I said, Barkan's method does not consider the damping effects. I will write here 0 time 0. Add. So it is assigned. It is defined. Now we need to assign. We have defined all the forces. Now we have to assign it to the model. So load case details. Add. I will make a load case. Name it as dynamic. Add. Close it. Select dynamic and add. So first of all, I will have to define the self weight. So I will have to assign the self weight in all the 3 directions, as we are going to perform time history analysis. So y factor is -1 as it is acting downwards. So add x direction, will make this factor 1. Add z direction, factor 1. Add. Self weight is defined. Now nodal force, the weight of the machine. The weight of the machine was 100 kilonewton. So 100 in y direction -100. We will assign it in all the 3 directions because we have to perform time history analysis. Fx, fy and fz. Add. Now time history, arrival time will shift 0. First force we have defined as 2.5 kilonewton. It was acting in vertical direction, that is Fy. add. The second force was horizontal force that acts in fx direction, add. Third one was moment that acts about z axis, so mz, add. We have to assign it. We'll select the self-weight and assign to view. Yes, self-weight in all the directions, self-weight in z, assign to view, assign. Nodal force, that is weight of machine, it acts at the CG of machine, so select the node of machine, assign to selected node, assign. And the dynamic forces are also generated by machine, so we'll assign it to the same node, so assign to selected node, assign. All the two forces and moment are assigned to the machine. The modeling of foundation, modeling of soil below the foundation, and assigning the forces are completed. In the rendered view, you can see the foundation. This is the foundation, how it look like. So it is ready. Now we have to go to command analysis, perform analysis. Okay, analyze, run analysis. So the analysis of foundation is done. We will go to dynamics. As we can see, the different mode shapes of the foundation. In the right side, we can see the table which shows the natural frequency of machine foundation. For all the 6 modes, we can determine the natural frequency of different modes or in different directions by watching the participation factor that is shown in this column. For example, we need to see the natural frequency in vertical direction. We will see the participation factor y, that is vertical axis. So here in this mode, third mode, it is 99.988. So the vertical translation frequency will be 21.89. Similarly, we can see the frequencies in horizontal direction as well as in the rotational frequency in about z direction. Next, we need to determine the amplitude at any point. So we will go select the nodes, and we can select any node over here, and it will show the amplitude at each node. You can select any node. Generally, in machine foundation, the amplitude needs to be checked at the point above CG at the top of the foundation, that is here. It will show 13. Also, needs to be checked at corners because the maximum vibration is at corners. In different softwares or in different versions of software, you will find some minute changes in the answers. So, and also if there is problem in any if there shows any error in foundation, you can also try it again and change the name of the material property. As I said, that sometimes when we keep the material name as rigid beam, it will not solve. So I will change it to rigid from because it does not allow the space between the in the name of material. So just change it and try it if you find any error. And so we can determine in this way, we can determine the natural frequency and amplitude of the machine foundation by finite element modeling. So that's all. Thank you for watching. Hope you would have liked this video. Thank you.